Hello everyone, my name is Divij Cody. I'm a senior here at UNC, and today I'm going to be sharing with you a little bit about Kras G12C. So shared to you here is the PyMol software. PyMol is a software that allows scientists or general researchers to visualize proteins on the molecular level, understand different regions in the three-dimensional level. So I work at the Campbell Lab in genetic medicine building, and I work closely with NRAS, which is an isoform of the RAS family, similarly to how KRAS is. The differences in residue between NRAS and KRAS lie in the allosteric lobe of the protein. This is the lobe known for effects. This is the lobe that has indirect effects on the nucleotide binding region, on the structural changes within the conformation. While here with my pipe straw model on this metal rack, I'm going to be explaining a lot about the effector lobe region. This is more of the direct effects of the conformation and kind of explains a lot about what the protein undergoes. So looking at residues 1 through 10, residues 1 through 10 go along the right to the left side of the protein, and that's kind of visualized here by the tan pipe straw going from my right to my left, your left to your right. Um, Moving on to residues 10 through 20, one of the more significant regions known as the nucleotide binding region. And this region is denoted in yellow, which kind of wraps back around and in towards the protein. And this red pipe straw actually indicates the mutation that we're specifically talking about, G12C. So the G12C mutation, as you can see, is directly on the binding region. And structurally, the impact of G12C creates a bulkier side chain, which disrupts the conformation of the P loop, and it sterically hinders gaps or GTPases from actually binding to that region. And as a result, GTP hydrolysis, a normal function of RAS proteins, gets affected. One more thing I'd like to indicate before I move on is there's another red pipe straw, and this is at residue 13. This is just a another common mutant found in KRAS. Moving on, we can see residues 20 to 30, once again in tan, and it kind of wraps around the front of the protein. Here is a green pipe straw, and it resembles a ball, almost a sphere. And this represents a magnesium ion, which binds to the protein. And when this magnesium ion binds to the protein, you're able to find a more stronger conformation and a more stabilized protein. So the magnesium's very pivotal for the stability of the normal functioning slash regulatory mechanisms of the protein. Moving on to residues 30 to 40 can be seen here in the green. The reason that it's green is because residues 30 to 40 mainly consist of switch 1 within the protein, the structure. Switch 1 is a highly dynamic region within the protein that's known to move around for different regulatory mechanisms within the protein during proliferation. Okay, moving on to residues 40 through 50. Once again, represented right here in tan. Moving on to residues 50 through 60. Kind of wrapping itself along the front and over is right over here in another green pipe straw. And as you can see, the two green pipe straws are meant to be close to one another to show interaction between switch 1 and switch 2, which does commonly happen in the KRAS G12C mutation. Another common side note, just a fun fact, that another red pipe straw is here on switch 2 because Q61 is a common mutant that occurs within these RAS proteins. So moving on from there, you're able to see kind of the structure of the protein overlaps itself a lot. It goes in and out a bunch. Uh, Here, the white regions are regions that I didn't want to emphasize as much, but those regions are the allosteric lobes, allosteric regions of the protein. Here you can see a kind of um, a helice, and sometimes there's also beta sheets. So if I can deselect these first however many residues, keep going, let's keep going, let's keep going. So after deselecting these residues, okay. For deselecting the residues, you're able to see this kind of helice right here, connected to kind of the strand, some of the strands. So this region is not as important in the effector lobe when talking about KRAS G12C, but it's important to note that the pipe straws identifying just these thin strands are not always going to be accurate because there's always going to be secondary structures. So, in talking about what KRAS G12 does cellularly, KRAS G12 causes uncontrolled cell division and ultimately hyperactivates the ERK pathway. There are stabilizing and regulatory mechanisms within the protein that clearly allows for proliferation even in such a mutated state. But organismally, KRAS G12C is a major driver of lung cancer, colorectal cancer, and pancreatic cancer. And tumors here become resistant to chemotherapy after long periods of time. But the important thing to note here is, although there's a bulkier side chain here in the nucleotide binding region, there are still regulatory mechanisms within the structure of the protein that allow for proliferation to still occur, and that is where you're able to see situations of cancer. Um, yeah, that's pretty much all I have to share. I'm going to stop share or I'm going to stop screen sharing just so a better visual of my model can be seen. And this is just maybe half, a little less than actually half uh, the entire genetic sequence of the RAS protein. So it goes in and out and wraps around as protein folding does. Thank you for your time.